At the United States Air Force Academy, we're always on the lookout for new and interesting ways to introduce our students to advanced computer science topics. As part of our introductory level comp sci course, we had students create a simple simulation of the Ingenuity helicopter as it takes off from the surface of Mars, hovers across the surface, and lands in a pre-designated location. In this video, I'm going to show you how we use this basic simulation as a starting point to create this, a more advanced version utilizing genetic algorithms. This version of the program is continuously training and evolving an agent that can efficiently take off the surface of Mars, map it, and land using a minimum of battery life and not having any human intervention whatsoever. I'll show you how we added additional complexity to the simulation to make it a more interesting problem to solve from an AI standpoint. I'll then show you how we use this simulation to teach students about the pros and cons of using AI to solve real-world problems. So sit back, relax, and enjoy the show. In order to make our simulation compatible with our genetic algorithm, we had to make several modifications to the student solution. The first modification we made was to add some dimensionality. If you were to watch the student solution over time, you would notice that it's fairly simplistic. For example, the simulation assumes that the drone only looks straight down regardless of its altitude. Additionally, the drone burns more battery life the higher it climbs, so there's really no incentive to go high. Finally, there are no random factors to consider, anything like wind or obstacles. Consequently, if you wanted to efficiently map the surface, there's really only one solution: stay as low to the ground as you can. To fix this, we added some additional layers. So the first thing we added was a field of view cone to the drone. The higher the drone goes, the more it can map, and this creates an incentive to travel higher and potentially burn more battery life. The next thing we added were wind layers. Each layer pushes the drone at a different direction or speed, which forces the drone to consider which layer is the best to navigate at. And finally, we added some randomization. After each run, we change the wind speed, direction, and size of each layer slightly. This will force our AI to favor a strategy that works in lots of situations rather than optimize for a single one. The second modification we made was to make the application run repeatedly. If you look at our reference solution, you will see that we have to restart the simulator after each run. But if we want to utilize machine learning, we're going to need to run the simulator repeatedly, hundreds, maybe even thousands of times, so that the algorithm can try out a bunch of strategies to see what works best. To do this, we added a new run simulation function to our program. This function resets the simulation so that we can run it multiple times using a loop. It also has parameters that let us control how the drone will behave during an individual flight. We can specify how much power the drone will use, effectively specifying how high it will go. We can also specify the coordinates that the drone will travel to in the right and left directions, as well as where it will begin the landing sequence. Finally, we can specify the power that the drone will use when landing, which tells the drone how softly to land. By manipulating these 5 parameters, we can, with a single line of code, define the strategies that the drone will use for each flight. This will give us an easy way to hook up the simulation to the genetic algorithm in the next step. The third and final modification is to integrate the genetic algorithm. At a high level, our GA essentially creates a population of different AI agents, each of which has its own flying strategy. Each agent gets an opportunity to fly over the Martian landscape with the same wind conditions. And when it lands, it's given a score based off of its performance. For example, the GA can be configured to give better scores to agents that use the least battery. Conversely, the GA might be configured to give a better score to agents that map the most to the Martian surface, or land in the designated area. It's highly customizable and makes for a great discussion point for our students. Once every agent is scored, our GA keeps the top performing members and uses them as parents to form new offspring. For example, given 2 randomly selected parents, we might decide to use the cruise power of the first agent combined with the landing power of the second. The resulting child is unique, but has characteristics of the best performing members of the population. We also add a few random members to the population. This prevents the population from becoming stagnant and allows us to run across new, potentially better agents other than the ones we started off with. This process of creating children, breeding them, and introducing new blood is called a generation. Our driver program runs the simulation over multiple generations. The only thing that we need to specify is the size of the population, the number of parents we want to keep after each generation, the number of children produced by the parents, and the total number of generations that we want the algorithm to run. With all of these pieces in place, we're finally ready to sit back and enjoy the show. In class, we'll let the students define their own fitness functions and train the algorithm while we talk about the machine learning process. The results of their training can sometimes be surprising to them. Students might try to optimize for battery life, only to find out that their drone immediately takes off and lands. Similarly, students may try to optimize for surface coverage, only to find out that their drone never lands in the correct spot. While we don't contend that our algorithm is a realistic simulation, because it's not, it does a remarkable job of emphasizing the challenges in coming up with a good fitness function. It also does a good job of highlighting the fact that even the best AIs make mistakes and can fail given the right conditions. This allows us to use the program as a starting point to talk about ethical implications of AI, especially in domains such as the military. Thanks for taking the time to watch this video. If you have any questions or concerns about our code, please feel free to reach out. Thanks again, and have a great rest of your day.